This is repeatable over long periods of time, over lots of operating environments, etc. And then you have a list of customers that then proceeded on from that. Started working in government spaces where security was ultimate. My responsibility in North America is working with U.S. entities, governments. In high security areas, it got deployed in smart cards. Very high security area as well. Then it went into FPGAs, which were used by government systems, or big carriers. Then we started moving more into low end, because this is not only very secure, it actually is very inexpensive to deploy. So moving it into wireless modules with Redpine, the Galaxy platforms, your phones from Samsung, we began deployment there. And then moving more into even lower systems, like as in Synopsys' ARC processors. And then eventually to sensors. Then there are MCUs that began deployed. Today we've shipped around 100 million units of devices out in the field. So that's quickly the story of Intrinsic ID. I'm going to go into the solution that you've come to listen about, and we'll continue Lance's story about how we deploy this out in the field. Okay. So we're going to create a triad of a solution. What we're deploying here is a SRAM PUF secure identity, SRAM PUF based secure identity in any of your IoT devices, which, by the way, if you're going to work with Amazon, AWS, it's a requirement. It's the third pillar. You have the network communication taken care of. You have the cyber infrastructure taken care of today. There's a lot of access controls to protect the data when it's in the data center. But you don't have a lot of mechanisms to protect your things in the field. So the identity would be that critical piece that we've provided. And we're bringing a government-certified level of security. This has been vetted by the governments and the secure industries and the EMV codes of the world. That was in the previous slide, I forgot to mention. But bringing it in a cost level that is just groundbreaking. So security doesn't mean adding cost in the situation. It means a much more simpler way of adding security. So with that, if you had these devices, the way this will work is these devices will have a microcontroller, and the microcontroller will have an SRAM. You would onboard a software module, and the software module will be connected to the SRAM. And from that SRAM, you can then generate a key that gets instantiated at that moment where you run and executed an algorithm. This key will be not known to anyone because it stays within the chip perimeter. It will not have been predictable to anyone, so it's a secret. It's really a pure secret. From this secret, you extend this into asymmetric crypto. You create a private key up to a curve, NIS256, then you create the corresponding public key, and then you get a certificate. And then you just keep following all the chains. So everything stays the same. We just have found a way to onboard the private key, and we also found a way to onboard, protect that private key, because this private key is not stored. This private key had been generated from the DNA of that SRAM, and then when you turn off the power, the private key is gone. We didn't inject, we didn't burn, we didn't permanently disconfigure the silicon circuits to have a key stored in it. Okay. How this works, this will probably be the core, and then I'll go into the demo, but this is really the fundamental explanation of how this works. What we're doing is we're leveraging Mother Nature, the principles of uncertainty, the uncertainty principles. Heisenberg, I think is the name. You don't control the parameters in manufacturing. You don't control the thickness of the oxide, the depth of the circuit. There's atomic differences. So in those atomic differences, you have a process variation. And we can't measure that so quantitatively, but we can actually observe behaviors that get affected by those process variations. And the behavior is actually the startup state of an SRAM. Okay. The startup state of an SRAM has either a 1 or a 0, and the contention occurs between two circuits that are trying to pull the circuit up to a 1 or pull it down to a 0. And based on the atomic differences of these circuits, you'll have a 1 or a 0 when it turns on. When you turn this chip back off and turn it back on again, you'll have a very similar set of ones and zeros. Any questions? Right, so that property, when you collect 1 kilobyte of those bits, you have enough entropy to create 256 bits of entropy, 2 to 256 bits of entropy, which will create a key. So from 1 kilobyte, it's about a 32 to 1 compression. We just run some algorithms, we do some error correction, and then we just hash and hash and hash until we get a very solid 256-bit key. And we then transform that key up to the rest of the protocol with crypto, to a private public key pair. But the essential beginning is just leveraging entropy, the uninitialized state of the SRAM, then to derive what is a puff key that is secret. Any questions? So with this, you have guaranteed uniqueness, because Mother Nature is not going to repeat itself. So that's going to be very, very, rare. You have the secret, and you also don't have a manufacturing step. You don't have a need to ask your chip vendor to inject the secret, use a key. You can be independent of that. Okay. You can control now when you decide to create your key that's used for your system. Your dependency is not on the manufacturer in that case. Yeah, so this has been certified. This has gone through a lot of vetting. We have gone through, because of the payment industry, testings with EMVCO and Visa. Common criteria is the FIPS version in Europe. We are working with FIPS in the United States as well. European governments, US governments have vetted this. So the FIPS is a level. There's a couple of testing. There's randomness, and then there's I think it's a level 4, but yeah. It's a pretty high level. And EAL 6+, we were the first in the industry to have 6, and that's the highest level of certification. So these are for very secure things. There are systems that you ship out of the country. They have to be protected for very important reasons. This is what the implementation looks like in a microcontroller. This is going to be an example with the Renesas chip. Renesas has their full CPU and their security infrastructure inside of it. It can authenticate and have an ID, and all those are great. You can use all those technologies inside of the Renesas part. In particular, there will also be SRAM. And the SRAM is really the fundamental thing that we need. We need to have 1 kilobyte of uninitialized SRAM. This chip that I'm talking about has 128 kilobytes, so we're using 1 kilobyte of the 128 kilobytes. You don't have to modify the silicon. You don't have to add anything. You just buy it as they ship it, right, with no special provisioning. Then you generate the secret with the SRAM, all contained within the security, electrical interface of the chip. It never leaves the SoC. There is an OTP storage there, but you may use that in the beginning for some purpose, but after you've created the puff-based key, you can actually jump that security and be independent of that. There doesn't have to be a relationship with that key. It's kind of like when you present your birth certificate, then you get your passport, right? You don't need your birth certificate anymore. Then here's some interesting attributes that I compare to other ways that you would do this. Because today the traditional way to do this is a key injection that you ask your manufacturer, or you actually buy a secure element from companies like Microchip or Infineon or ST Micro. So in the different categories, you have security. I think from a security perspective, the secure elements are considered very high security. It's actually a very strong, hardware-protected, tamper-proof packaging of a key. However, you have to take that contents of that chip and control and have an interface with the microcontroller, right? So you're outside of the microcontroller's security perimeter, so you do need to protect that channel. So we would argue that in the case of SRAM Puff, where everything is contained within the security perimeter of a microcontroller, it's more secure than if you were to use a secure element that's decoupled from your main microcontroller. But it in itself, as a package, is very secure, the secure element. And that's been around for a very long time. Key injection is now taking your chip. Now you have to use a more sophisticated chip that has OTP, and then you have to provide some logistics. How many do you want to buy? And then you ask the manufacturer to key it for you. Right? So that would be considered low because what you're doing is you're burning keys in fuse or flash within the system. So there's all kinds of ways now today when you have a fuse or flash to understand what those bits are. Depending on the state of attack, it's actually a very pretty trivial thing. So that would be considered lower security. The other part that we compare is the flexibility and the ease of gaining the keys inside of the chip. You can program a puff key in any different stages of your manufacturing process. You can ask the chip vendor if you want. You can ask your distributor or your system contract manufacturer who's assembling your board, or you can even do it out in the field, depending on your manufacturing flow. Because it's actually execution of a software on an SRAM at any time that will then create the key. But in key injection, the mechanism for key injection is on a wafer, so it has to be done at the time of your chip manufacturing. Then you have to blow the fuses right at that time. If you have special circuits in your chip, you actually can blow the fuses when the chip is already packaged, so you can do that at the contract manufacturer. But those are limited, and the secure element, the keys are packaged only in the chip side. Right? You assemble this on the board, but you don't have any control on the keys when you do it. And the other big difference is just the cost. You ship about 50 million units, you pay under $1 million. If you want to buy a secure element, you pay $7.5 million. It's just a big difference in cost adder. Our model is a software business. Any questions here? You can get access to such because of the nature of what we do is all about an SRAM. It can run on any architecture. We run on Intel, we run on Qualcomm, MIPS. These are the instruction sets, RISC-V, Synopsys, and ARM. Neos, even an 8-bit CPU have also supported it too. So it's quite agnostic in terms of where you can apply this kind of security on your systems. And then with Renesas, we already have done the pre-integration and vetting. So the work that needs to be done here is the installation of a 20 kilobyte software module, but doing it securely. Using all the hooks, security hooks of the chip to make sure that SRAM is protected, make sure that the broad key code that gets put there cannot be changed. There's all these security requirements when you integrate our code into a chip. Okay. So that has been done with the RX, with the Synergy, with a lot of the MCUs that we provide with Renesas. So today you can buy a chip and you'll have ready binaries that you just use to go off and running. And if you don't use Renesas and use something else, there is a process for doing that porting, which is about a couple weeks. Okay. I'm going to move this down to the demo. I mean, could stop for questions, but I'm going to just demonstrate actually how this would work in a manufacturing flow. Okay, again, we'll have a preloaded broad key is the name of our product. It's got the elliptical curve algorithms to extend a key into a private-public key pair. And we'll have an SRAM. So the code will execute. It'll read the SRAM. Yeah. Again, this is any time in the manufacturing stage. We would then create a private key as a result of the execution. Little detail is about 1 million cycles. 1 million cycles later, you'll have a key, a unique key that won't be repeatable by any other device. Then we extend that to a public key. And then the public key gets sent off to the GlobalSign IoT platform. Okay. The GlobalSign IoT platform would process it, When it gets sent, it's already in the form of a certificate signing request, CSR. So GlobalSign will process it and then come back and sign it. It may do a challenge. It may do whatever it decides to do that's appropriate for security. And then the certificate comes back and is stored into the flash. This whole process is what is needed to create the identity of the device. Okay? It's a very, very fast round trip. Let me give a quick show of that. So I connected up a Renesas RX231 board. It's connected via Wi-Fi. It will be serially connected to my PC so I can do the provisioning. Okay, so my PC will be acting as a IoT. Is that too loud? Maybe you should turn it off. My PC will be acting as the IoT platform that's on a manufacturing device that's used to do the provisioning. So, wait. It's not plugged into my USB. Okay, so I'll reset the device. So this already has a key that's programmed into it, and now it's accessing the Renesas cloud, and it's going to be sending data. The point about the data that gets sent, it's authenticated. When you're on the cloud side, you know that this is data that came from this device. There's a mutual TLS protocol behind that to create that assurance. Right, so now it's just finally connected. But I'll start from the beginning. I will remove I'm wiping the device, so now it's a blank device with no programmed key into it. So this process is pretty simple. These will be steps that are added into your system manufacturing. When you are loading your software, you run diagnostics onto it, it'll be just one of those steps. So you would then, in one of your test vectors, send a command to the IoT platform to activate the SRAM. So as I said, the SRAM is going to be read. This algorithm will be computing a private key. Then we would extend this private key to a public-private key pair. So that would be done. And then we would export that public key. Yeah. So this is the public key generated. The private key now is inside of the flash, inside of the MCU. But that public key is a public key. We need the certificate authority to make it mean something, to be able to trust it. So we would create a certificate signing request and send that off to the service. So this would be GlobalSign. This is going out to the GlobalSign service from my PC, if I have good internet, and there it came back. Yeah. So that's the certificate. Now I can install that into my device. So I'll reset my board. Now this is going to be running on the Wi-Fi of this. This board is going to reset. It's going to start to access the Renesas cloud. And you'll see in the Renesas cloud, I have an account. It'll be presented a certificate. Then the certificate will be used to challenge the device, authenticate it, and then allow it to be, I'm gonna have to pardon the Wi-Fi connection. But that's the whole round trip. This now is authenticate data being sent to the Renesas cloud platform. We have this working with AWS and Microsoft Azure. There are kits that come that allow you just to download, put the whole embedded software package on your MCU, and then we'll provide you the tools that allow you to do the whole round trip to the AWS and Amazon clouds using certificates. Okay, so it's working. You'll start to see data coming in from this device. Yeah, so I got it every 5 seconds. I can even warm it up here and you'll start to see it getting hot. I'm not lying. Yeah. Yeah. Any questions? Miss Shula. Is that it? Sorry. This is a bare bone. The question is which RTOS? It's a bare metal. It could be any RTOS. The place that this runs is within a crypto library, and the crypto library can interface to the OS in any way. Yeah. It's a good question. C library. The implementation is a C library, about 20 kilobytes of code size. Million gates for execution of creating a key, and 500,000 cycles, not gates, cycles for reconstruction of a key. Yes, sir.
I'm just curious about the process of studies going
Yes, yes, that's a great question because it is very relevant. Electrons drift, and the property of the SRAM could change so that the fingerprint could change. That is correct. We actually implement an anti-aging algorithm. So the biggest contribution is something called, I forgot the name, N bias. So if you do a reverse bias of the actual startup and just apply that, it starts to reduce the error and it starts to get cemented in the direction of that original startup pattern that you enrolled. So we see this, and we tested this in aging accelerated programs for up to 30 years, which is required by government. So we see that the error rates actually go down over time. Never goes to zero, but it just goes down over time. You have a question, Ben? Thank you.
Thank you for watching this GlobalSign presentation. For more videos on identity and PKI, follow one of the links on your screen. And don't forget to subscribe to our channel to keep up to date with the latest video content.